Hi, today I want to present a new pipeline called OpenVCP 1.0, which stands for Open Source Vaccine Candidate Prediction Platform Version 1. And to give you a brief background about the pipeline, the prediction of antigenic determinants, or so-called the epitopes, is an important element of vaccine development. There are many tools available that are built specifically for the purpose of epitope prediction, and these include IEDB tools, NetMHC, NetTCR, and BEpipred. These are tools that are renowned and are well used by the academics. However, many of these tools are open only for academic use, and their licenses are restricted by the paywall, which means if you're non-academic or from a business background, you have to actually pay to use these tools. And our research over here aims to actually build an open source modifiable platform for predicting vaccine candidates. And here is an example workflow that we're using in the pipeline right now. And this slide is specifically for the epitope selection step. So within the epitope selection step, we start from the antigen of interest. For example, SARS-CoV-2 S protein. So we've downloaded the sequence of proteins from the GSA database. Then what we do is to actually give a binding prediction. So we have integrated 4 different platforms in here, binding prediction platforms in here. First is the MHC1 binding prediction. Second is the MH2 binding prediction, BCR binding prediction, and TCR binding prediction. And the tools we use are MHC Flurry and CNN Pepred, LBEEP, and Titan, respectively. The Titan may be dropped in version 1 due to its computation time and compatibility issue. So after we've ran all these prediction tools, we will try to find a consensus sequence. We're currently planning to use either CD-HIT or MAFFT algorithm. I will explain these in the later slide. So theoretically, the best vaccine candidates would be the linear epitopes that are able to bind aptly to MHCs, TCRs, and BCRs. After the epitope binding step, what we're expecting is the table like this. In this table over here, I borrowed from the publication that shows you the rat and mouse peptides. These peptides are being aligned together to form a consensus sequence. And this consensus sequence is what I've told you in the slide before in the workflow. So what we're expecting in our results is to actually put the predicted peptides for MHC1, MHC2, TCR, and BCR together, and we will try to align them together and to form a consensus sequence. Through measures such as multiple sequence alignment using MAFFT or MAFFT algorithm, or clustering by similarity using the CD-HIT algorithm, we will try to find the consensus sequence of peptides that would best represent the candidate vaccine. So what is up next after the epitope selection? After successfully finding the candidate vaccines, what we're going to do is to actually validate it by molecular simulation. And this is a workflow that is continuation from the epitope selection step. After we got the selected epitope, what we'll do is to actually get the PMHC, which is the MHC bound to the peptide, 3D structure from the PDB. With the 3D structure of the MHC, what we're going to do is to actually replace this peptide, whatever it is, with the selected epitope. Then what we'll get is the PDB file of the epitope plus the MHC. And then what we're going to do is to do the docking simulation using the AutoDock and dynamic simulation using the GrowMax tools. And the end result would be the 3D structure of a predicted vaccine candidate bound to MHC, as well as the relevant statistics if the peptide is actually well binding or not. Through molecular docking and dynamic simulation experiments, we will try to visually portray our predicted vaccine candidates binding to the MHC molecule. To wrap it up, OpenVCP 1.0 aims to provide completely open source vaccine prediction tool that not only academics but also non-academics and businesses can make full use of. Although the primary goal of developing the pipeline is due to meeting compliance to the Infectomics project, the developed pipeline could be later used in the research for vaccines against cancer and senescence. And that was it. Thank you.